I was tasked with scanning one object on campus of my choosing and turning it into a 3D point cloud. This would be accomplished with LiDAR, that being light detection and ranging, a process where a laser and a camera are used to see how far away an object is. In my project, I used a red laser attached to a 3D printed chassis along with a Raspberry Pi, that being the microcomputer and not the food. In addition, a camera was mounted on the 3D chassis for the detection side of it. From there, this tripod-mounted system was connected via Ethernet cable to my laptop, so it could use real VNC to access the Pi's user interface. With that said, it didn't exactly come right out of the box working. Even after assembly, 3D printing, testing, and troubleshooting, I still had to write code and calibrate it. I began calibration by carefully taking pictures at distances every 6 inches, so the system could see what those distances looked like. From there, I manually adjusted values in the analyzing code to match the expected results. These expected results come from the fundamental LiDAR equation, which is what my system uses to process these images. Of course, when I say it like that, this whole process sounds pretty quick, but in reality it consisted of quite a few stress-filled nights with failed testing and seemingly endless troubleshooting. At the time, I felt like I was putting Murphy's Law to the test with seemingly endless problems. In the end, due to a mix of faulty equipment and my own ignorance on how to safely handle these components, I had to buy 2 Raspberry Pis, 2 cameras, and 2 SD cards. I also had to restart my progress on the software side no less than 3 times due to completely corrupting my Pi's operating system. For a while, I was running my Pi off of a USB stick instead of an SD card just to keep my testing moving along. And even that just brushes past the countless minor issues and points of confusion I faced throughout the journey. As you can imagine, these challenges were not great for my wallet, or my cortisol levels, but it was certainly good for my knowledge base and determination in the face of challenges. With that said, let's get back to the task at hand. I had to select a good target to map, and I quickly singled out 3 that looked interesting. A rock, a fire hydrant, and a handicap sign etched into a pillar. While the rock would be cool to map, it was kind of small and wouldn't provide enough data given the lack of precision in my setup. Likewise, the fire hydrant looked cool, but between the bright lights overhead, constantly passing cars, and the reflective black paint, it would be a nightmare to get the software to recognize any data. In the end, I went with what I've been calling the obelisk. I was hopeful that the data would be able to showcase the handicap symbol and the slope top, but before I could find out if it would, I had to finish testing my system. Having gotten everything fully working, or so I thought, I began to try and scan a chair, but quickly ran into some problems. It wasn't fully in frame for the camera, the black chair legs weren't being spotted, and the resulting data was seemingly random. I came to realize that I had been trying to scan with a vertical laser instead of a horizontal one like my processing code needed. So with that revelation, I instead mapped a paper bag, and after some code adjustments, I was beginning to see some interesting results. By taking the image, cropping it, and looking for values within my chosen range of hues, saturations, and values, or HSV, I could get an image that just shows my laser. The code then uses this new image to make calculations, along with a manually entered angle that the picture was taken, about the distance from the camera to the target. This is heavily reliant on the calculations from earlier. After some fine-tuning, I was able to compile the results into this point cloud, which I was really excited about. You can even see each wrinkle in the handles in the bag. With the testing complete, it was time to start mapping my target. In the early hours of midnight to 3 a.m., I set out to start collecting data. The reason I went out so late was to be absolutely certain that I was avoiding the sun. This is because, as an introverted engineering student slash vampire, I am terrified of sunlight. Oh, and I suppose sunlight also introduces background noise, which can mess up my data collection, so that was an added bonus. Arriving at my destination, I began the process of collecting data. I had to carefully adjust my tripod 1 degree at a time, with a level app on my phone giving precise angle measurements for me to ensure that I was no more than 0.2 degrees off of my target angle. Due to how the code worked, I was scanning in increments of 1 degree at a time, which resulted in some spaced out data and challenges in the field. For my first scan, I was too far away, meaning a change of 1 degree up or down on my tripod covered a lot of vertical distance. The result was that the data was even more spaced out. Thankfully, after receiving the blessings of a drunken wizard with a staff made of beer cans, I was able to map the front surface of my target and head back to my apartment. After some more fine tuning on the software side, I was able to generate my first usable point cloud of the front of the object. Unfortunately, the handicap symbol wasn't clearly visible and appeared more as an absence of data due to the spacing between the lines. Furthermore, the tip of the obelisk wasn't visible given that it was only at a roughly 5-degree incline, which my camera, positioned near the ground, couldn't see. Regardless, I ventured back out, and over the course of 2 nights, mapped my target from the back, sides, front left, front right, and back right. I wanted to see if I could get the corners to line up with the flat surfaces in the final comparison. This was very time consuming, as I had to be extremely careful when aligning my tripod. I knew that putting it at the wrong angle could really mess up my data. Not only would there be a gap in the data, but the code accounts for the change in angle, so the entire row would be rotated. In the end, due to having to record the data multiple times, I was out there for a few hours both nights. Recording the data from behind was particularly challenging and uncomfortable due to having to set the tripod up on and sit on a bunch of rocks. Despite this, I was able to record some good data and went home happy, ready to take on the data analysis. Once I had all the data, which the code compiled as a bunch of text files, I was able to use a software called Cloud Compare to view the data and compile it into a final 3D point cloud, that being a whole bunch of little points in space that looks like a 3D object. Unfortunately, the sets of corner data were not quite at a 90-degree angle, meaning that they would visibly stick out if included in the point cloud. So I unfortunately had to discard that additional data. Either way, I was able to reach the culmination of my work this semester, a virtual box with somewhat odd proportions. This was a little disappointing at first, but I realized that it isn't just about the result. I learned so much while doing this, and the data isn't just a box. It's a real object that I scanned and analyzed, and that's pretty cool. To finish out the project, I attempted to turn my point cloud into a 3D model, first by using a software called MeshLab, then by using a dedicated 3D modeling software. This process was also a bit of a struggle and resulted in a rather odd outcome. But just like before, it was about the process of learning, not just the result.